Okay, in light of Newton's laws, the three laws of motion and the law of gravity, we need to revisit Kepler's laws and make sure we understand what's really going on, because Newton's laws showed that Kepler's first and third laws were almost right. What you'll find in your educations, whatever major you happen to have, whatever you specialize in, you will learn that progressing in that field of study, a large part of that is being told or realizing that what you learned before is not quite right. It's maybe kind of right, mostly right, right in certain circumstances, approximately right, but not really right. And that's the case with Kepler's laws. Newton's laws showed that Kepler's laws were approximately right for certain situations, but weren't universally right in all cases. So we need to revise laws 1 and 3. So Kepler's first law, okay, should be rewritten this way. The orbit of a planet around the sun is an ellipse, so that is correct. That is perfectly right. Comma, with the center with the, not the sun, but the center of mass of the sun planet system at one focus. Okay, this demands some explanation. The pink part, right? It shows up pink, it shows up nicely actually. The pink part demands some explanation. Used to read the orbit of a planet around the sun as an ellipse with the sun at one focus. But now we have this weird pink phrase, the center of mass of the sun-planet system. What is the center of mass? Well, I'll show you an example of what I mean by center of mass. Here we have a meter stick. Okay, I'll hold it down about this high so you can see it in the video. And I'm going to put a weight on either end, about 2 centimeters from either end. So there's one weight, and here's another weight right there. Notice that with those two weights on the meter stick, I can balance the meter stick by putting my finger in the middle. Is that showing up good? Yes, in the middle. Okay. My finger is at the center of mass of the two-mass system. Think of these like two planets, or two stars or whatever, two celestial objects. My finger is at the center of mass of those two objects. Now suppose that I double the mass of one of them. Now where's the center of mass? Well, it's closer over this side. I need to see if I can find it here. A little more. And now the center of mass is where my finger is. It is not in the middle. My finger is at the center of mass of the two-mass system. Okay. So suppose you took the sun and the planet, say Jupiter. Say that's the sun and that's Jupiter. Where, if I connected the sun and Jupiter with a really long, thin stick, where would that stick balance? Not in the middle. It would balance over toward the sun, right? That point at which either these two masses balance, these three masses, or this one is, actually let's call it two. This is a mass of That's twice the mass of that one. So it's a two-mass system. My finger is at the center of mass of the two-mass system. Okay? And every planet-sun system, it's called, has a center of mass. And that is what is located at a focus of the ellipse, not the sun itself. Let's draw a picture of that. Okay? So if we have two equal masses, then we have two orbits that might look like this. There's one there. That's one orbit. So it goes like this, down there like that. That's one mass in its orbit. See, the other mass in its orbit might look something like this. Now here's a case where we have two masses which are about the same size. This point in the middle here is a common focus. We have two ellipses, and that point is a focus of the pink ellipse and of the yellow ellipse. And these two planets are going to go around. They're not going to be at that location. If this one was up there, the pink one would be down here somewhere. Okay. These two planets are going to orbit each other, but they're not orbiting each other, they're orbiting the center of mass. Now suppose we double the mass of the pink planet. Okay, so this is mass of pink equals mass of yellow. Now let's say that the mass of the pink is twice as big, is 2 times the mass of the yellow. In that case, what we would have is we would have the pink orbiting on a smaller ellipse like this, still an ellipse, and this one would still be large, okay, and it'd still have a common focus right here. All right, so if the pink one's there, the yellow one would be out here somewhere, going around. So now the mass of the pink one is larger. Notice that the larger the mass of the pink planet is, the less it moves. Okay. If it's a very light mass, it's going to move a lot. If it's a very large mass, it's going to move less. How about if we had the sun and a planet, say Jupiter? So what if this is the sun? And around the sun was orbiting Jupiter. The sun would not stay still. The sun would go on a little bitty ellipse. It would go on a little ellipse that looks like that, while Jupiter went around it. In other words, the center of mass of these two planets is right there. The common focus is the center of mass of the sun-planet system. And all sun-planet system means is that collection, the sun and planet taken as a single object, as a single system. Okay, so that is the center of mass. The common focus is the center of mass. Common focus is the center of mass. In this case, the common focus might be about right there. It turns out for the Sun-Jupiter system, the center of mass is right about at the surface of the sun. So what happens as Jupiter takes its 12-year orbit around the Earth, as Jupiter takes its 12-year orbit around the sun, Jupiter swings out in a big circle, but the sun just does a little wobble. Just a little wobble like that. Okay? Because what the two bodies are orbiting around is not the sun, but the center of mass of that system. And the center of mass of the Jupiter-Sun system, if I took Jupiter, put it here, okay, room here. If I took Jupiter and put it here, and the sun, and put the sun there, the center of mass would be really close to the sun, so close to the sun that it would be like right at the sun's surface. So the sun just makes a little wobble like that every 12 years as Jupiter swings way out around it. Okay. The second of Kepler's laws remains the same, and the third one changes. And all I'm going to do is write it down. We're going to come up and have a lab in a couple weeks, maybe even, I can't remember if it's next week or the week after, in which we deal more closely with this version of Kepler's third law. I just want to write it out for you. Remember before, used to be that we had p squared equals a cubed, right? Well, it's been revised because of Newton. It's revised to being p squared is a cubed over what we call m total. M sub t is the total mass of the sun plus planet. Okay? Total mass. And the units are solar mass units. This I'm simply giving to you now so that when we come back to it later, I can refer back to it. Okay? Because this particular version of Kepler's third law shows up in at least 2 labs that are coming up, and I wanted you to at least see it so that when it comes up in the lab, you'll know you'll be able to refer back to this. Okay? The main thing for this video is simply this. Okay? Masses are equal. They're both going to have equal sized ellipses. But if the masses are unequal, the larger mass has the smaller ellipse. And if the masses are really unequal, as in the case with the sun and Jupiter, then the sun just does a little wobble like that, while Jupiter swings way wide. And of course, the same with Earth. The effect of the Earth on the sun is very tiny, but it is there. And the sun has a little wobble because of the Earth too, but it's way, way, way smaller than Jupiter's. Jupiter gives the sun the biggest wobble because Jupiter's the most massive of all the planets. All right? All right, so what's up next? Well, we're going to finish up with this idea of gravity, talk about why it's called universal gravity, and I'm going to draw you a really cool picture coming up next.